Okay, so we start with the IDF limit. Okay. All right. I would like you to see these two functions here. First, observe two functions. Say it's just x plus 1. Okay. And the domain is the whole thing, right? Natural domain. And the second one, like to put this one here. Okay. So the domain here is you can put any x except 1. So except 1. Okay. But if you do some simplifications a bit, simplify, that means the thing is you can do some factorizations. All right. And on the domain, x not equal to 1. Is that in this rational form, the forbidden thing is just x cannot be equals to 1, right? So, but that's outside the domain. So for x not equal to 1, you can cancel this one. Right? Cancel those. So you end up with the x, sorry, should cancel this one instead, sorry. You cancel this, right? So you end up with the same as this one, but this is for x not equals 1. Okay, and what if you try to graph functions? Graph functions, then you just get this one here. Okay, and for this is the y equals f of x. Okay, and for the second one, see that's the same, except here is 1, except it's not defined at 1. So here, instead of there, you have a hole there, right? Let me just there. Okay, so you see that f and g are the same except at x equals 1, for which g is not defined at equals 1. Okay, so you compare. Okay, for x, for everything except 1. Okay. All right. So we see that everything's the same except this one. Okay. So let me just introduce two terminologies. Okay. If you have a function, say given a function f, okay, and okay, I would say behavior of f at x equals a, and behavior of f around x equals a, except itself. Okay, so what I would like to do with these two notions, so the key is yes, at and around. At means that at a certain point. Okay, so exactly at the point x equals a, and this is around. So just except at x equals a itself. So just near x a. So this is near x equals a. So this is the, for example, for this one, we would call it this behavior at a is just f of a. So that means a is in the domain. Okay. So around a is that, what about, so if I point this one, behavior of f at a at 1 is this one. The value is just, let's see, it's x plus 1. This is 2. Okay. But you see, what about behavior of g around 1? So you cannot say behavior of g at 1 because this is not defined. Okay. Example. So fg as above. What I call behavior of f at x equals 1 is f1 equals to 2. Okay, but what about g? We of g at x equals 1. This is g1, but g1 is undefined here. But at least we can say something. What about behavior of, this is undefined, so we cannot answer this one, but we have behavior of g around x equals 1. Okay, so around x equals 1, what are you looking at actually? We're looking at values of g close to x equals 1. Okay. Here is observing values of g of x when x is near near 1. Okay, so what can we say about this? Well, it's, we say that, well, it's close to 1, to 2, because this is supposedly 2, but somehow we have a hole here because 1 is undefined. Okay, are you with me at this point? up to this point.
Yes, sir.
Right. Near. So we see. All right. So this is the idea of limit. Actually, we would distinguish between behavior of f and at a function and f around a function. Sorry, around the point. Okay. And what we do here, the term near or something, that's quite relative. So we would do some approximations. We will do some approximations. Okay. So this is the idea of the limit, actually. All right. So let me just tell you another story. Let's see. All right. So suppose you're say a police or an agent, something, supposed to observe for some person. Say, or an intelligent agent. Observe the person P. Okay. So what would you do is, well, you're supposed to know about P. What you don't want to do is just P, ask P, interview P directly, because that's what you not supposed to do. But you ask around people around P. Ask, interview people around. So you start asking questions from this neighborhood, from P's friend, right? So getting closer, getting closer, getting closer, getting closer. Hopefully you can gather informations that gets closer, and so with the hope that you gather informations about P from the observations. Okay. So conclude about P from the informations around P. Okay, so you're not asking P himself or herself, but asking the people around. All right, so you see the idea? And but the problem is that what's the people around P, the informations you gather from the people around sometimes does not match the real person, what P is. Okay, so that's another issues, whether the information gives you an accurate description of P. Right? So the question is, how accurate the description of P from people around. Right? Okay, hopefully as it gets closer and its P gets more accurate. Okay, so that's the storyline of this limit. Okay. All right. So back to this one. Back to the function g is minus 1. Okay. Or g not equals to 1. Okay. So the questions now is, well, for sure, this is undefined. But supposedly it is defined. Can you describe what G1 looks like? Suppose it were defined. Okay. All right. So at least we can say, well, G1 is near to dot dot dot. Okay, so that's the questions. So now the idea is, so this is behavior of G round x equals 1. Okay, and this is these notations here is summed by these notations. Limit of G as x approaching 1. Okay. So you see that just from the picture, okay. So even though G1 is undefined, but you see that the value, if it were defined, it's close to the number 2. From this picture. Close to value 2. Okay, and this is what we call limit. Okay, so this basically answer, well, get an idea of what limit is. Limit is a, say, a value which is approached by behavior of functions around some point. Okay, so the tendency of the functions around that point. Okay, so this tendency of G around x equals 1 is 2. It's close. Okay, so that's the idea. Let's compute that. Do some computations. Just okay. So let's some example. Okay, so the thing here is that this limit here, limit of x equals to 1 x cubed minus 1 over x minus 1. Okay, so these notations is actually asking if you have functions, for sure it is not defined at 1. So the question is, sorry, but what about, the question is how f behaves near x equals 1. So, or you can say around, sorry, I should use to around or near. Okay, so we compute the values of fx x around 1, and we ask whether where it is near to. Okay. All right, so let's see here. Let's do some commutations. We can simplify this because we can factor the x cubed minus 1 out because it's binomial. Okay, you can factor this out. And the rest is, remember this kind of decompositions, binomial decompositions. You have x, you have 1 over x minus 1. And if you assume x not equals to 1, and so this is not 0, you can cancel this. Okay. So you end up with x squared plus x plus 1. Okay, but this term now is defined for x equals 1. X squared defined for x equals 1. So it is okay to plug in the value x equals 1, right? And the value is let's see, when you plug in 1, you get 3. Okay. Okay, so we'll see. If you graph this, let's do some more manipulations a little bit. Okay, what we do here is this one. So we write this down as x. Look at just this one, right? And so this is 1/2 squared. Okay, so let's see, are those the same? But for sure, no, because when you square them, you get x squared. All right, that's the same, and you get twice of 1/2 times x. So just get x. Right, so you get the two first terms, okay, but then you have 1/4 from the square of 1/2. So you subtract is 1/2. Right? So this is the x squared plus x. The trick is known by completing the square. Okay, so we'll use this often. All right, so then we still have this 1 here. All right, so this and this are now the same. Okay, and the thing is, we can rewrite this as x plus 1/2 squared and plus 1 subtract 1/4, so 3/4. Okay, so this is a parabola. Let's see, because this is positive, so this is opens up with vertex. Let's see, this tells you vertex. This tells you vertex. All right, so that's the graph of the parabola. Let's see, so we get 1/2, negative 1/2. So that's the vertex. So the parabola looks like this one, right from there. Okay, and the thing here, except at x equals 1. So, not good. This is x equals 1, which is, well, just say something like this. Here, you have a hole there. Okay, and when you plugged in 1, the value here supposedly is, let's see, this is 3. Yeah. Okay. So what the question is, even though G1, sorry, F1 is undefined, but at least the values near 1 is 3. Okay, so these are the conclusions. Even though F1 is undefined, but the values F close to 1 is 3. Okay, and in terms of limit, x equals 1 of, what's the functions? X, sorry. This is our f. Okay, so then that's what the limit is. Okay, and it's not always the case. So the near or around a point, for example, let's say this one. Okay. So, all right. So let's see. So the question is, let's remove this one first. Okay. So the question is, how is the behavior of f near x equal 0? Okay. All right. So let's graph the function first. To the left of 0, the value is -1. There's a hole. And for x positive, there's a hole also there. Okay, so this graph. Okay. Now, the question is, so we know that f1 is, sorry, 0 is undefined. So you question whether, what the values around x equals 0? Okay. All right. So if the pictures look like this, and you can see that, well, from the left, it looks like -1. Right? But from the right, looks like 1. So that's something that you cannot resolve because two observer give a different answer. You see, if you're an observer coming from the right, you would guess that the value should be 1. But an observer coming from the left see this as, well, supposedly the value is -1. We're coming from the right. Guesses that the values of f nears 1. But coming from the left, guess that's the -1. So that's something that you cannot resolve. Then you can say something is you just cannot decide. Sorry. Behavior of f near 0. And we say that this limit does not exist. Okay. All right, so that's one case. We would say later on, this is the limit from the left. This is, sorry, limit from the right. This is limit from the left. Okay. And one other thing is that, let's see, this is more realistic. So suppose we have a function sine x over x. X not equal 0 because that's undefined 0. Okay, if you if you plugged into your calculator, okay, okay, so the value of x near g near x equals 0. So this is the value of x. This is the g of x. Okay, so sure is not 0. So you can say this from 1.1.01 001 gets closer. Okay, and the thing here is that if you try to plot the function, you see something that looks like this one. Well, I just let's see. Oh, sorry. I should say I postpone this example later. Right? Postpone this one. Instead, I will be looking at these functions. Okay, this for x not equal to 0. Okay, so you can think, well, if x near 0, then 1 over x is large, right? So just like you can say this a black hole, right? So you're curious, what about the values near the black hole? Okay, the values at the black hole is undefined here. But what about the values near the black hole? Okay, so then what about this one? All right, so you see that, remember that when we discussed last time, when you write something like this is frequency, right? The bigger the number, then the higher the frequency, the more waves you have. So if you have 1 over x, okay, if x is large, so 1 over x is small, then you see that this is low frequency. Okay. When x is small, though, as x close to 0, near 0, 1 over x is large. So what can you say about the frequency? Hello.
High.
Well, frequency?
Higher frequency.
High frequency. And you see that as x moving to the closer to 0, say this is frequency, say 1,000, but here it's 1 over x is getting smaller and smaller. So what can we say is that as x closer and closer to 0, the frequency gets higher. So it is just makes sense if I picture this as, let's see, sine, the maximum is 1 and -1, right? And at 0 is undefined. So say this is frequency S, and it gets very messy around here. right? Because it's very high frequency. And same thing here because it's an odd function anyway. Okay. And you try to resolve this by, let's do some zooming out, sorry. Let's do some zoom out. Okay, that means you bring your microscopes and try to get the picture. For example, this is still 10, for example. Now you get not 10, but just 1. So from here to here, you bring a zoom by a factor of 10, for example. But the thing here, you get the same thing. So it's still messy around 0. Okay. So in fact, you can try to do some zoom out even bigger and bigger, the zooming factor, but you still left with the same picture. Okay. So similar with this one. So, this kind of behavior, we call this extreme oscillations. All right, so that's the question is, back to the questions. So what's the value of f tends to? Is there any value which for x for which f getting close to? Okay. All right. If you pick a value on top of this, you seems like to get closer to 1. Right? So for example, if you, let's see, if we pick something that looks like this, let's do some scratch. Okay, so sine x is, say, let's use x. Sine, say, t equals to 1. So t should be, the value should be, let's see, sine is, okay. So this pi over 2, and you add a multiple of 2 pi. Okay. All right, so that's t here is our 1 over x. Okay, so say 1 over x, so t. Okay, so here x is p over 2 plus 2k. Looks like this one. Or you can say, how do you compute this one? We take the p out. For k, right? So this 1 over x. So then x is 1 over this. Okay, so if you choose your k to be this one for, so this is xk. You can plug in k0 plus minus 1 plus minus 2 plus minus 3. Okay, So from here you compute that f of x of k is always 1 for all k. Okay. And you see that xk, as when k is getting larger, when k is getting larger, then what happens to this one? Xk is smaller, close to 0. So what does it mean pictorially is that when you this is xk, this is another xk, right? So you're jumping around the top of the waves, right? So you see that, well, if you're an observer jumping around the top of the wave, you looks like going to the values 1. Similarly, an observer just jumping around this at bottom of the wave thinks that it should be close to -1. And an observer just staying at the bottom here at 0 will thinks that it's close to 0. Okay, so there is no single number so let me just tell you this here. First observer on the top of sorry, this is observer 1, top of the wave, thinks this should be goes to 1. This is observer 2 at the bottom of the wave thinks it should be -1, and another observer here thinks that should be 0. Okay, and those observers cannot agree on just one number. So observers cannot agree on single numbers. Okay, so in this case, we say also its limit of sine 1 over x as x is close to 0. This does not exist. And let's go back to our simplest idea in the beginning. Here, right? This one. Observer from the left, sorry, from the right, says that, well, it should be close to 2. Observers coming from the left says, well, I agree, this should be closer to 2. Then the limit is 2. Okay, but in this case, this is also true. Observer coming from the right say this should be close to 3. From the left also, from the left agrees, say this also 3. Okay, so the limit is 3. But this one, 2 observers coming from the left and from the right and from the left cannot agree on a number. So this does not exist. Okay, and this one also, well, they cannot agree on a number, a single number, where the function tends to those numbers, because every observer here give a different numbers. So in this case, we say that limit does not exist. Okay. All right. Well, any questions? All right. If not, we stop here for say 5 minutes, and then we'll explore again uh, the notion of limit with some computations. Okay. Stop here.